Okay, so let's go ahead. First of all, we are recording, if it is fine for everyone, we are recording this webinar, so it will be online in the next days. So don't worry about recording it by yourself, we're already doing it. Okay, so I'm going to share my screen. Well, I'm going to control my computer on the other office by remote desktop, so I hope everything will be fine with the internet connection. Okay, so this is the outline of the course today. So we had the introduction to OpenSees and to STKO, so you know that STKO and OpenSees are two different softwares. So OpenSees is the solver, STKO is the user interface. And this is what we're going to do this morning. So I just realized here I made a mistake. I talked about constitutive models twice, both in the morning and in the afternoon. So actually, I will talk about the constitutive models in the afternoon when we will be doing micro modeling. And now we will start with model with a brief introduction to the software, so you will understand how the user interface works. And to do this, we will start with modeling of the simplest element that you may have in OpenSees, which are beam columns. They are the simplest element from a geometrical point of view, but there are many things to take care of. And we will talk about it, talking about how you can do the distributed plasticity approach and the lump plasticity approach. You know,
so maybe there is still some noise. Maybe you have to disconnect the iPad. The iPad.
Probably one. Yeah, let me try to
connect the audio from the iPad.
Okay, let me try. Okay, can you hear me better?
No, now it's way worse.
Yeah, because
you have to choose one of the two microphones.
I switched off this one, but it's still working.
Yeah, you need to switch off from Zoom.
Okay, just a second. Okay, now it's still working, this microphone.
Take it in another room, we are fine.
Okay, Guido, can you hear me now better?
Yes, now it's better.
Yeah, because I had to switch it off, because even if I switched off the audio, it was still working. Something is happening to this microphone. Sorry.
Much better. Now it's perfect anyway.
Yeah, much better. Yes.
Okay, let's go ahead. So we will start giving an introduction to the STKO user interface, talking about beam column elements. So I will explain you how to do this simple model, this simple column, and how distributed plasticity works in OpenSees, and how the lump plasticity works in OpenSees. There are two ways of doing this. And we will talk about the problem of strain localization in this kind of models, what's going on when you change the element formulation from one another. Well, everything at this point is one-dimensional, so we are going to use uniaxial material models. Then I will move, always in the topic of reinforced concrete structure, I will talk about how to model shear walls. In shear walls, we will move to the triaxial case, so we're going to use three-dimensional possibility models. I think we have something in the chat. Okay. I'm going to show you how to use these three-dimensional possibility models. So I will give a brief introduction about the three-dimensional possibility models that you may have for concrete and masonry then. And you will learn how to use shell elements for these shear walls. So you will learn how to create nonlinear section, layer section for shells, where you can use nonlinear models for concrete and steel rebars and all this stuff, and how to join beam and shell elements together, so the model will get slightly more complicated. Then in the afternoon, we are going to use the same material model, but for masonry. So I will talk once again a little bit about how to calibrate the material model parameters, this time for masonry. We will start with a micro modeling for the in-plane behavior of a masonry shear wall. And then I will show you how to do an homogeneous modeling step instead of the micro modeling, using first an isotropic nonlinear model, and then something which is called orthotropic mapper, which is a kind of material adapter that takes the isotropic material model and makes it orthotropic. Then tomorrow, Wednesday actually, Wednesday morning, we will move ahead. So we'll still be talking about Masonry. This time I will start with a micro modeling for the out-of-plane behavior. So here I will give you some extra information about how to deal with the out-of-plane behavior in micro modeling and in OpenSees, because there are some tricky parts to understand about the shell element formulation available in OpenSees. And then we will do the same of an equivalent homogeneous model using the orthographic mapper for the out-of-plane shell. And then at the end of the Wednesday meeting, I'll be talking about a little bit on how to handle large models. So I will give a brief introduction on the parallel version of OpenSees, how to use it, how it works, and how STKO will allow you to use it. Because now these parallel versions are kind of not very well known, because it is very difficult to use them when you try to write input files for OpenSees manually. But with the help of STKO, now this becomes possible. So I will dedicate the last hour of Wednesday meeting for this. Okay, so now let me give a brief introduction on the user interface, so now you can navigate in it, and then we will start with the first example. So first of all, here you have two tabs, the preprocessor and the postprocessor. They're pretty similar with different commands, so you can move between one and the other. Remember that in the preprocessor, basically you create your model, you run the analysis, but then you don't have to wait for the analysis to finish. The preprocessor and postprocessor are two completely different things. So you can work in pre-processing something while you can post-process something else. Okay, so there is not this problem that you have to run the analysis and wait for the analysis to finish. Then for each one of these two, you have the typical menu bar with all the commands. This menu bar is also replicated here in the ribbon bar, where you have all the tabs with all the toolbars. Then you have a work tree that has basically everything that is in the document organized in a hierarchical fashion. Then you have a terminal here, which is basically where STKO gives you some information or asks you something. And here you have an input line, like any CAD, where you can input your comments, okay? Or for example, when you want to input a distance or a point. So this is pretty easy. And finally, here you have the graphical interface. Of course, when you install STKO, you have a documentation, so you can see how to move into this CAD, but it's pretty like any other CAD, so you should feel comfortable to model with it. Perfect. Now, a second point that I would like to remark, because a lot of users always find it kind of difficult, because when it comes to preprocessor for finite element solvers, you have basically two kinds of user interfaces, of approaches for the input file. The one that is called Orphan mesh approach, which is basically the approach that you can find in software such as SAP or ETABS or MidasGen, where basically you draw nodes and elements directly. So you don't work on a geometry and then you discretize it. You directly input the discretized model. This is fine when you just do frame members, because basically one member corresponds to one finite element, so it is kind of fine. But when you have to do more complicated models, continuous models, surface or solid models, this is kind of difficult. So here we choose a different approach. We start with a CAD model. As you can see here, we can draw lines, surfaces, solids. So we work on a continuous model. We apply materials to it, we apply boundary condition on surfaces, on solids, and so on. And then at the end of the day, just before running the analysis, we mesh it, okay? So keep in mind this particular point. Okay, so I think now we can start with the very first example. So in the first example, I will show you how to create, or how to understand what are the available elements and possibility models for modeling beam structures, so beam and columns. The first thing, we will start with a simple column. We will do a simple pushover analysis of just one column using the distributed approach. And then we will see how you can do the lumped plasticity approach in OpenSees. Okay, so we can start with the geometry tab. Okay, perfect. So the first thing that you want to do is to create a column which is 3 meters high. Oh, another note. In OpenSees, you don't have the concept of unit system. So you have to be consistent, okay? And the same for STKO. You have to be consistent. So, for example, in these examples, I decide to model with Newton for forces and millimeters for geometry, for spatial dimension. So here I'm going to model a 3 meters high beam. So when you issue a command, every time you issue a command, you have some input from the software that tells you, okay, this is what you have to do. And you can do it graphically. So for example, I want to pick the center point here. Then you can move it, or you can use the input file. So for example, I can input the second point manually. That can be 0, 0, and 3000 in the Z direction. Okay? Right click to accept the command. So this is the typical thing you do for every kind of modeling. Now, if you have seen, I didn't draw first 2 vertices and then the element that connects to them. I just modeled a line, because a line in a CAD environment is already a curve which connects 2 vertices. So the vertices are already embedded into this line. That's why you don't have to make the mistake of creating points and then a line. Otherwise, you will end up with a beam and 2 separated nodes, okay? Okay, so let's say this is the process of creating a CAD. Now this is very simple. We will see more complicated models later on when we will be doing the shear wall model. Okay, so once you are done with the geometry, you can move to the next step, which is interaction. Now interaction is actually something that is used to connect disjoint geometries. Now in this example, which is very simple, we have just one geometry, so we don't need any interaction. But interaction are basically those tools that are used to create kinematic constraints between incompatible geometries or to create contact conditions, cohesive zones, and so on. And in this example, we don't need it. Then you have definitions. Definitions are typically used to create what in OpenSees is called time series. Time series are basically the load multipliers. So in this example, since we are going to do first a vertical analysis and then a pushover analysis, we just need one linear ramp, which is a monotonically increasing load multiplier. So the first thing that you can do, of course, when you issue this kind of commands is to go through the toolbar. For example, here we are in property. You can create a definition here or on the worktree. I personally prefer to work on the worktree rather than switching between different toolbars, but it's up to you. So you go here and you click add. Now, every time you want to add something which is connected to OpenSees, like the definition here, you have this interface, which is pretty similar for all the other steps. The first thing that you have to do is to choose a name, which is not mandatory, so we call it ramp. And then you choose a model. This one is one of the OpenSees models. For example, under definition, we can have 2 kinds of models for OpenSees, which is a friction model, when we don't need it now, or the time series. Time series are used to define load multipliers. So you have many kinds of multipliers, the constant multiplier, linear, path, which is the standard one, we will see it later, and then some utilities for ground motions and so on. Now, since we're going to do pushover analysis, so we just need a linear ramp. Linear ramp is something that goes from time 0 to time 1, from a multiplier of 0 to a multiplier of 1, linearly increasing, pretty simple. Okay, then every time, now I'm going to explain you this, but this one will be the same for every kind of component in OpenSees. So you choose the model, and then here you have you have a tree with all the attributes of that model. In this case, it is pretty simple. You have just one attribute. Whenever you click on one of these attributes, you have the description for these attributes and a link to the OpenSees documentation. So if you are not aware of what's going on here, or you want more details, you just click here and you go to the OpenSees description for this, okay? To the OpenSees manual. If you're already familiar with OpenSees, basically you will never do this, but that's fine. So here we just created the load multiplier. Since we're going to do a monotonic pushover analysis, this is enough. Next step, physical properties. Now this is a concept that I want to make also clear in STKO. Physical properties are basically every tools that define the constitutive behavior of your model. So here you can find materials and cross-sections. Materials just for solids, cross-section for structural elements like beams and shells. So let's say physical properties is what defines the constitutive behavior. And this is the same thing you find in every finite element user interface. Later on, you have something called element properties, which is kind of similar, but here you just define the finite element formulation that you want to use. So let's say this one defines the kinematics of your geometry. In many softwares, you don't need to specify what finite element formulation you want to use, because basically those softwares just have one finite element formulation for every geometry. So if your geometry has 2 nodes, he knows that you have to use a beam, just one particular beam. In OpenSees, you will see that you have many finite element formulation. So that's why you have to choose which one you want to use. So let's start with the physical properties. Now here we want to do a distributed plasticity. Now distributed plasticity is often connected with the concept of fiber section, but this is not necessarily true. Distributed plasticity means that we are going to use a finite element formulation which has Gauss points all over the member length, and each Gauss point can have a nonlinear behavior. Now this nonlinear behavior should be defined in terms of beam stresses versus beam deformation, and it will be integrated over the length. That's why it's called distributed. So it is not necessary to be a fiber cross-section, but in this example, we will be doing it with fiber cross-sections. So what are the steps to create a fiber cross-section for a beam? Now, the first one, of course, is to create uniaxial models. So the first model that we are going to create is a concrete 1D. Now we'll show you one nice thing that we have here in STKO, and that can help people understand how this material model works. So as before, you choose a name, which is random, then you choose a model. This time we want to do a material. In OpenSees, materials are divided into 2 groups. The uniaxial materials that are one-dimensional. So they are those that can be used either with trusses or with fibers in fiber cross-section. And then you have the ND. ND stands for n-dimensional. That can be 2D, 3D, or 3-dimensional positive models. So for the moment, we need materials. We want to create some material for concrete, and here we have many of them. Now, the simplest one that we are going to use in this example is concrete 01, which is a Kent-Scott part for compression with zero tension. Okay, now let's say you're new to OpenSees. If you're new to OpenSees, you don't know anything about these parameters. So when you go over one of them, you can see the description. For example, this one is the compressive strength, input as negative. If you are not sure of what's going on here, you have the, as I said, the OpenSees documentation. But many times, this OpenSees documentation is not enough, because yes, you see what these parameters mean, but you don't really understand how they affect the behavior of your model. Now, in this case, it is very simple, but sometimes it is not so obvious. So let's see what you can use here. Here you have the material test, which is a tool that allows you to calibrate the material parameters just before running the analysis. So you are sure not to make any error at the constitutive level. So in this case, the concrete compressive strength, for this example, we choose -35 megapascals. Then also this one should be input as negative, which is the strain at compressive peak. Then you have the residual strength, and you want to make it -5, and the ultimate deformation. Now, as you can see here, this is one of the main problems with all the material models you have in OpenSees. You cannot specify fracture energy. You have to specify the ultimate deformation. So this already tells you, if you are familiar with the problem of strain regularization and mesh objectivity, you already understand that you have to calibrate these parameters according to the mesh size. And you will see now what happens in this kind of models. Then when I will be talking about the shear wall, I will introduce our own material model that has the automatic strain regularization, okay? Fracture energy regularization. Now for this example, I just choose an ultimate strain of 0.015. And then let's say you want to make sure how this material parameter works. So here you have material tester. You can do either monotonic material tester, like I choose a monotonic strain profile. You can choose the number of division, the target strain, that can be, in my example, 0.02. And let's push it. Okay, so this is the behavior in compression. And they say, okay, but I want to see how this material behaves in a cyclic loading protocol. So you can use one of them. You can use this one, for example, from the Eurocode. I choose a number of division. Okay, you can choose the target strain. Now for this one to work properly, this one should be the peak strain. And you can choose, for example, now this one, as you can see, symmetric, both in tension and compression. You can say, okay, no, but in tension, I want to push it slightly more, slightly less. So let's say 10% of compression. This one will adapt, and then you do a test. Okay, so you understand how this one works in a cyclic environment. So you can see that is a mix of plasticity and damage. The unloading is not perfectly the elastic one, but it's not the second one. So you have both inelastic deformation and stiffness degradation. And as you can see, you don't have any response in tension. Okay. Then there are many other complicated models that you can try to work with. And I will show you, it is very nice, this kind of material tester, to understand how a material model works. So let's say this is fine for my concrete. So I accept it. Now the second step, I need steel. So let's go for the steel. Let's call this steel. Once again, we go under model, materials, uniaxial, and this time we want to find a material from steel and reinforcing steel materials. And here we choose this steel 02, which is the Giuffre Benedetto Pinto material model. Okay, let's see how it works. Here you have to input the strength and cell strength. So for this example, we choose 487. Here you have some parameters that define the cyclic, the aesthetic behavior of this model. There are some default parameters. If you go on the website, you will find that some default parameters can be something from 10 to 20 here, and then 0.925 and 0.15, and then you can play with them to see how the shape of this thing works. This one is instead is the linear hardening. In this example, I've chosen 0. Perfect, and then you have the elastic modulus that I've chosen to be 205,000. Okay. Once again, we want to understand how it works. I want to see in cyclic behavior, and I want to push it a little bit more than this. Can you do the test? And this is how it works, okay? Now, for example, you don't know what this parameter means, so let's try to increase it. Let's put it 50. Here, as you can see, you have a slightly less rounding of this kind of envelope. This one is the Bauschinger effect. So basically, it is telling you that probably a value of less than 20 is better. As you can see, this is the difference, okay? Perfect. So please take advantage of this material tester because it is very useful. It can help you spot a lot of problems just before running the analysis. So okay, here we have the steel. So now we are ready to create the fiber cross sections. Now, as you know, in OpenSees, you have some tools for creating the fiber cross section, but it's not so comfortable. You have to input the fiber either one by one or creating quadrilateral regions. But then you will see that creating a fiber cross section by hand is not so easy. In STKO, you have 2 different tools for creating a fiber cross section. Now, the first one, it's the most general one, where you basically have a small CAD. Let's see here, you go under section, you choose fiber. Here you have an editor, and you can draw everything here. So you can draw small cross sections with any shape. You can do a mesh, a Delaunay mesh of that surface. So you can draw basically everything. But this one will be kind of a waste of time because you have to redraw your section every time. So that for rectangular cross section, we created an automatism, and this is why the programming part of STKO is so nice. You can create automatisms for things that you want to do over and over again. So you create it once and then you have it already. So for example, we created a rectangular fiber section, which is not different from the fiber cross section of OpenSees, but it is only on automation. It has many automated things, and I will show you. So okay, I go under the rectangular fiber cross section, and as you can see here, you have a lot of different parameters. You still have a fiber cross section here, but this one is built automatically based on these parameters. So For fabric cross-section, one thing that you have to do is to input here the torsional constant times the shear modulus. Before it was optional in the previous version of OpenSees, but in the new one they changed it and it is mandatory, so please use it in 3D. And for this beam we have already calculated 4.2 e to the power of 13. Okay, then you can choose the dimension. It can be 2D or 3D. In this case we are going to do a three-dimensional model. Then you choose the shape. In this case it was 500 width, okay, and the height of 300, 20 of cover, which is fine, and then you can choose the number of rebars. As you can see, it will change here. So I've chosen 18 diameter for the corner rebars, just one for each corner, 18 for the bottom, and the bottom we want 3 rebars. 3 rebars also at the top, and then only 2 rebars at the lateral side, 2 and 2. Okay, and so basically here you see them changing accordingly. And now comes the interesting part: material parameters. So first you can choose the rebars, and we choose the steel parameter, and you can, as you can see now, it gets colored with the color you have in the uniaxial material model. Then you do the same for concrete. For concrete you have 2 materials, the cover and the core. Now let's see what happens if I just choose the cover. I choose concrete 1D for the cover. Here you see an automatic computation. Basically, if you choose a material model for the cover, but you don't choose anything for the core, STKO will automatically compute a confined version of the same material that you have chosen for the cover, and it will put it here in the core. Now, this one, of course, will depend on the confinement model that you choose, the computation of the lateral pressure, and of course, the stirrup layout. Now, the stirrup in OpenSees are not used, so they are just fake numbers here, just used to calibrate this confinement. So if you don't want confinement, you can either input manually a material model for concrete here, so you will not see anything. If instead you want automatic confinement, so this automation that we put in STKO, you can just put known, and so it will calculate it automatically. Of course, the properties for the confined material model will change as soon as you change the stirrup layout. Now, in this example, I want an 8 diameter, and you see it shrinking. Now, let's increase a little bit the spacing to 100. Once again, you see the difference. And then the legs in Y and X direction, I choose it to 2 and 2 each one. Okay? And then, of course, you can change the strength of the steel you would like to use in the stirrups. Okay, so this is just to say that the nice thing about this scriptable interface is that this one, for example, is not made by us. It was made by a PhD student that was working with STKO and decided to create this automation. So it is pretty useful if you know Python and if you know how to code. And you can create tools that can be reused by everyone. So it is pretty useful. Okay, so this one is the way you can create a fiber cross-section. Perfect. So now you have learned uniaxial material models, fiber cross-section that will basically give me now the PMM interaction for my beam. But this is not enough. Specifying the fiber cross-section is not enough for a beam, because this one only gives the behavior at one Gauss point. But since you have many elements in OpenSees and many integration schemes, you also have to define how the Gauss points are laid out in the element. And this one is what is called beam property. You can find it under model, special purpose, beam column, beam section property. That basically is nothing but how to distribute this fiber section along the element. So you have many options. First, you can choose between the integration groups. That can be the standard integration types. Then you have user-defined, for example, when you want to put integration point wherever you want with a different cross-section in every integration point. Then you have a few others that I will explain later on. Now, by default, for distributed plasticity, choose the standard integration types. And then in this group, you can choose between the others. You have Lobato, Legendre, Radau, many others. Now, by default, you can choose Lobato, which is what is mainly used by everybody. And the default number of integration points are 5. You can choose any point according to the Lobato scheme, starting from 2. Now, in this example, we are fine with 5, because 5 integration points using Lobato scheme along a beam, which is 3 meters, gives me an integration point at the bottom and at the top, which has a weight of 150 millimeters, which is kind of a good value for the plastic hinge zone. I will explain you in a while why, because this is important. So let's say 5 integration point as the default, and we choose the fiber. Okay, so this is okay, perfect. Now we need to we have the beam fiber, perfect. Now we just need to select this one, and we drag and drop the beam property. Okay, perfect. So now we have, you can see the extrusion if you are in the property tab. Otherwise, if you go in the geometry tab, you don't see it. Okay, so when you work with constitutive models, you typically move to the property tab so you can see the extrusion and the material colors here. Now in this example, actually we want to push it in along the X direction, okay? And we want the strong direction of the beam to be along the X direction. So how do you do this? Now, it is not necessary in this example, but I will show you because this is important when you do more complex models. Many times you just want to orient a beam cross-section. So you can either change this cross-section, but it is not optimal because maybe you want to use it in both directions in your complex model. So you have something called local axis. Local axis is a way to define the local orientation of the beam. So for example, if you want to see how this beam is oriented by default, you can switch on this button that shows the local axis. And as you can see, the Z vector is pointing, let me switch off the faces for a while. The Z vector is pointing by default along the positive x-axis. And I would like to turn it on the other direction, okay? So to do this, I can go to local axis, I click add, and I can create a new local axis. A new local axis can have 3 kinds of definition. It can be rectangular, cylindrical, or spherical. And in this case, we just need a rectangular local axis. We press OK. And here we have all the instructions. So the first point, the center for the local axis, which is not important in a rectangular local axis. Then you can move to choose the X direction. And now we choose it using the orthogonal constraint. Where is the orthogonal constraint? Okay. We choose it in this direction. Okay, so that the X is pointing, the Y is pointing along the X. And then we click a third point, okay? So let's go on top to make sure it was fine, perfect. So now what you have to do, this one is just a definition of the local axis. Now you can just select this beam and you drag and drop the local axis, okay? You drag and drop it and you release it. Okay, now basically this local axis has been applied to this beam, replacing the default one. So now the Y direction is pointing in this side. And as you can see, the section has been turned on the other direction. If I do a Control-C, you can see it, okay? And Control-Y to reply it. Okay, so now you've learned also how to use local axis and how to create a geometry and how to define all the constitutive behavior of a beam. Now the next step is to define the element property. So the element formulation that we want to use, and so the kinematics of the element. Why do you need to do this? Because in OpenSees you have many elements, especially for beams. So let's call it beam, and we go under model. Here you have all the groups of finite element models that you have. Now we want to choose elements for beam columns. And here you can see you have many of them. The most important are the displacement beam column and the force beam column. Okay, displacement beam column are the standard one that are based on the displacement formulation. So the strains are compatible with the displacement formulation, and the stress is automatically computed from the strains. This is quite important because if you choose a displacement beam column, keep in mind that the solution will not be correct if you use different models or if you use strongly nonlinear material models, because you cannot have localization only in one portion of the beam. So you need to discretize the beam in many elements. That's why it is important to understand the integration weight. While instead, on the other hand, if you choose the force beam column, the force beam column enforces a profile for the internal forces, while the section deformation are computed to satisfy this equilibrium. This is the opposite instead. Since the deformation are not forced to be continuous along the integration points, it happens that you may localize in just one integration point. That's why it was important to understand the weight of the integration point, okay? So in this example, I choose the force beam column because I don't want to discretize this in many pieces. Okay, so when you choose an element, here I can choose between 2D or 3D analysis. We are doing a 3D analysis. And here in transformation type, you can choose linear, P delta, or co-rotational. This one is basically the kinematics. Now, in this example, we are not doing geometric nonlinearity, so we keep it linear. Okay, and as we did before for the physical property, we just select this element and drag and drop the beam element formulation. So now this geometry has both the physical property definition and the element property definition. Now let's save the model. So we go ahead. So day one. And here I already have the RC column. Now in this example, I'm going to create another folder, and I will send you by the end of the day the material, all the files that we already did in the RC column. Okay, let's call this one model. Okay, perfect. Now we can go ahead. Now the next step, as you can see here, are the condition. So I want to move on the condition tab, so I don't see anymore the section extrusion. I don't need to see the local axis because they are fine. So here I will see all the boundary conditions that I define. Now in this section, you basically define boundary condition and you assign them to the geometry, but you are not telling OpenSees when to use them. In the analysis. You have to do it later on. So first we are going to define all the boundary conditions that we need in this example. Now the first one, of course, is the fixity at the bottom. So let's go fix bottom. And here we go under model. We want to apply a constraint. Here we have two groups, SP or MP. SP stands for single point constraint, and MP stands for multi-point constraints, so kinematic constraints. Here we just want to use a single point constraint, which is a fix, and we have to specify that we are in 3D, and we are using what kind of degrees of freedom set we are going to use. There is standard displacement, displacement and rotation, or displacement and pressure. Now in this case we have displacement and rotation, and we want to fix them all. So I check all the degrees of freedom that I want to fix. And now, as you can see here, STKO says, okay, choose a model, set its attributes, and then select the entities this condition will act on before closing the editor. So I want to apply this condition to the bottom, okay? So I select the bottom node here, and I press OK. Now, as you can see here, now I have the symbol of this condition right in the bottom. Okay, next step is to apply a vertical force. So vertical load. We go under model, loads. Here you have many loads. You have forces, which are basically nodal forces or distributed forces that will be converted to nodal ones. Otherwise, you have beam loads, thermal and mechanical loads. And then you have single point constraint, which is an imposed displacement. Now, in this case, we choose a nodal force because it is simply a column. And it will be minus along the z direction. So this is the vector of my nodal force along the z direction of minus 20 kilonewtons, so 20 E3. Perfect. And I decide to apply this one on the top node. So click on the top node and press OK. And here you can see the force acting on it. Third step, the last boundary condition that we have to apply is an imposed displacement on top. So here you can either choose an imposed force and do a displacement control, or as in this case, because I find it more immediate, apply directly a displacement and do a load control analysis. In this case, I'm going to add an impose displacement. So let's call this push. And I go under model, loads, single point, prescribed displacement value. Once again, we are in 3D and 6 degrees of freedom. And I want to apply a displacement at the X. Now, keep in mind here you have an option which is called relative. Here you have the description. If you check on relative, then the displacement that you apply here will be relative to the current displacement in the analysis at the time this condition is applied. Now, we don't need it now, but I will show you how this is useful in the shear wall example in Masonry. So for the moment, let's keep it always not relative, so absolute value. And I want to push it up to 25 millimeters. Okay, once again, I select the point where I want to apply the boundary condition and press OK. So also here I have my condition. Now, as I told you, here you just define the boundary condition, but the order in which you define them is not important because they are not yet in the analysis. In fact, here, the last step that you have is called analysis steps. Basically, it's where you define all the pieces, all the stages of your analysis and how they work in an history. So which come first? Okay, so the first thing that I typically do is to define a recorder. A recorder is something, by default, OpenSees does not record any results. So you have to specifically ask for a result to be recorded. If you don't put any recorder, you will not see, you will just run the analysis, but you will not see any result. So the first thing that I do is to create a recorder. So you can go under model, and here you can find recorders. And you just have the MPCO recorder, which is our own recorder, that basically writes the output for STKO. It just will write a single database. So you can go here, you just type the name of the database, and in my case it can be results. And then you can choose what nodal results you want. Okay, for this example, we just need displacement and reaction force. We can also ask for rotation and reaction moment, but we don't need it in this example. That's just to show you. Then you have another option which is called time option, the record frequency. By default is always. So I want to record every step in my analysis. Otherwise you can choose, I want to record every tiny increment or every number of steps. Now, in this example, since it is quite small, we can safely record all the increments. Then you have the results on the elements, okay? And here it comes a tricky part of OpenSees. I will try to explain you. Nodal results in OpenSees are well defined, and there is a fixed number of nodal results that you can have. You can have displacement, rotation, velocity, and so on. There are no custom results for nodes, but elements are different. Any elements can have its own results. So here what we did is to try to collect a number of results that are typically asked for, that are available basically for every element. And then if you want to ask something that is not available in this list, but you know that you're using an element or a material model that has this particular result, you can do it in the custom vector. And I will show you later on with our material model that has extra results. Now in this example, it is sufficient to record section forces and section deformation. Section forces and section deformation are basically the forces at the Gauss points. While instead here, force and deformation are forces and deformation at the element point. So for a beam, forces and deformation are actually the internal forces of the elements and the basic displacement in local coordinate system. While for a beam, section force and section deformation are the axial force, bending moments, and axial deformation and curvatures, for example. Then you may have other options like material stress and strain that are used by solids. So in this case, we don't need it. And for beams, you can also record strain and stresses in the fibers. So here you can see section dot fiber dot stress. It means I want to record stresses on every fiber of every section, and every section means every integration point of the element. So let's say that we want to also visualize stresses and strain in every fiber. Okay. Then you have another option, which is region. For example, if you want to restrict your results only to one portion of your model, let's say to keep your output database small. Of course, in this example, it is not important. Okay, so this is the way you define the output that you want. Now let's start creating the analysis stages. Now, the first thing that I want in my analysis is to apply the fixity condition at the bottom. So I click Add, and I call it Add Boundary Conditions. And I choose Under Model. And under Model, you have something called Pattern. A pattern is basically a load group or a constraint group. And this pattern can be added or can be removed from a certain stage. And in this case, we want to add it. Then you have many patterns. The typical one is the load pattern, which is the typical load case you have in many other solvers. Then you have the constraint pattern, or something called uniform excitation or multi-support excitation that are for dynamic analysis. Now, in this case, we just choose constraint pattern. And here you have two groups, single point constraint and multi-point constraint. Each one of them is a vector. So you can say, okay, at this point of the analysis, I want to apply just one boundary condition, which is the single point at the bottom. So I make room for one. So now this one is a vector of just one entry. And I choose the fixed bottom. And I press OK. Okay, so as you can see now, I have a vector of 1 here, a 0 multi-point constraints because I don't have it. So I press OK. Now at this point of the analysis, OpenSees has a recorder and has all the boundary condition applied. Then third step, I want to do the same, but to apply the vertical load. So add vertical load. Once again, it is also a pattern, as I did before. Is a pattern that I want to add, but this time it is a load pattern. A load pattern is slightly different. I still have 3 vectors here, one for loads, one for element load, and one for imposed displacement. Now in this case, it is a nodal load, so it goes in this vector here. And as I did before, I have just one entity, so I create room for one, and I select the vertical load. Okay, then the next thing that I have to choose is this TS tag. TS tag is the time series, which will be basically the load multiplier for this load case. Now, this load case contains just the vertical load that should be applied monotonically increasingly. So I just choose the linear ramp I've created before, okay, which is this one in definition. Perfect, this is fine. This one is telling me that I have this reference load that will be increased from 0 to 1. Perfect. Now that I have a vertical load, I can do my first analysis, my first stage of the analysis, which is the graphic analysis. So I click on Add, and let's call this Gravity. This one is an analysis, so I go under Models, Analysis, Analysis Command. And here you have many things. If you're familiar with OpenSees, you know them. So the first type is the analysis type, which can be static or transient. In this case, it is static. Then you have the constraints, the constraint handler. This is kind of new, this is kind of particular in OpenSees because in many software you do not specify how the software internally treats the boundary conditions. But in OpenSees you have to. So if you want to make sure, you can typically use the penalty method, which works with almost everything basically. It's the only one that works with everything. Otherwise, you have some limitation. The plane constraints, for example, cannot be used with imposed displacement or with constraints which are not diagonal. So, for example, a rigid diaphragm. Transformation can be used with everything because it applies the transformation of the stiffness matrix. The problem is that if your model is very complex and you have many overlapping conditions that defines basically an overly constrained model, this transformation method may not work. It may skip some of the constraints. For example, if a node is involved in a multi-point constraint and then in the other, it will be used only one of them, and you don't know where. Okay, while the penalty, since it is basically a fake stiffness that imposes approximately the constraint, it will be applied anyway. Otherwise, you have the Lagrange multiplier, but it transforms your system matrix. It is not positive definite anymore. It has more degrees of freedom. And if you have overlapping constraint, this will really create another constraint model. So I typically choose always the penalty method. Penalty method has some drawbacks, however. The penalty method works with very high stiffness to impose the constraint. This stiffness should be high, but not so much. It should be enough high to impose the constraint, but not too much to make the system ill-posed. Now, in this example, basically what you can do is to estimate the stiffness of your model or a characteristic stiffness. For example, in this case, I have my Young modulus is kind of the order of 1 to the power of 10 or to the power of 5. Then to this number, you add 8, which is half of the precision of a double number. Okay, so you can go to the power of 13 to 16 in this example. I found that 1 to the power of 16 is fine. Perfect. Now the next step is to specify the number. So is how the system of equations are renumbered. Now don't care about this unless I will be talking about this when we will be doing a parallel analysis. But for the moment, just keep the default one. Then the system. System is basically the linear equation solver. So if you know what you're doing, you can change it. But you have to know what you're doing. Otherwise, the default is a solver that is fine for sparse matrices and non-symmetric matrices. If you know the kind of problem you are doing, you can change it. For example, I know that I'm working with a profile symmetric positive definite matrix. I can take advantage of this one, which is faster. But if you don't know, you can choose either super LU or UMF path, which are both useful for non-symmetric sparse matrices. So by default, I choose the UMF path. Then you have the algorithm. The algorithm is how you solve a set of nonlinear equations. The default is Newton, but also here you have many of them. In this example, I was using Newton, yes. Then you have the convergence test. This one instead can be found in any solver, of course, so you are familiar with the test. The test is basically what tells you when the solution is converged. Now, by default, you have the norm unbalance. The norm unbalance is the norm of the residual. So the norm of the internal forces minus the external forces. The problem is that when you use the penalty method, you cannot use this one. Otherwise, this kind of residual will never go to 0 due to the penalty components. So when you use penalty, make sure you choose the norm displacement increment. So you check the displacement increment instead of the force. Now, in this case, 1 to the minus 4 millimeter is fine. You can change the number of iterations, let's say to 1000 or 100. If you want to know how your nonlinear process is going, if it is converging or not, in OpenSees you can use the print flag that basically tells you how many information you want. So if you put 0 by default, it doesn't print anything. So you don't know if it is converging or not. If you put 1 and you have all the description down here, I'm hidden it. Okay. You have the description here. If you put 1, it means print the convergence rate. so basically the number of iterations and the residual. And this is what I want to print. Perfect. Now, at the end, you have the integrator. Integrator is basically how you move from one step to the other. So how you integrate your equation. Now, in this case, I want to use a load control, which is fine. And I want to use 10 increments of 0.1 increment each one. So at the end of this analysis, I do 10 steps, 0.1 multiplier each step. So at the end of this analysis, I go to the multiplier of 1, so the complete vertical load. Okay. Now there is an option in OpenSees that is quite nice. It's called load constant. So after this analysis, I want to keep all the previously defined load, which are basically those applied here in add vertical load. I want to keep them constant. Keep them constant mean later on they will not change due to the load multiplier. They will remain constant. Once I do this, I can safely reset the pseudo time to 0 instead of going. So in this way, basically, you don't have to define many ramps. For example, in the next step, I have to apply impulse displacement. With any other solver, you should define 2 different ramps. One that starts from 0 to 1 and the other that goes from 0 to 2. And this is kind of annoying when you have many stages. In OpenSees, instead, you can choose to say, okay, but the previous load, I want to keep them constant so that I can safely reset the pseudo time step to 0. In such a way, the next loads can be applied with the same time series I used before. Perfect. So this is the gravity analysis. Now the next step is to apply the horizontal load. So add horizontal load. Once again, I go under pattern, add pattern. This time is always a load pattern. As I said, I can reuse this ramp because now the time step has been reset to 0. But the horizontal load is not actually a load, it's an imposed displacement. So I go here under SP, I make room for one, and I choose the push, which was my single point constraint here, the imposed displacement. Press OK and OK. Fine. The next step is to define the analysis for the horizontal load, which is the horizontal analysis. Now, since it is very similar to the gravity one, we just need to change a couple of parameters. Instead of creating it from a new one, we can just clone it from the gravity and change some parameters. So I call it pushover, and it is still static, penalty is fine. UMF pack here, if you want, let's say here I'm going to have some more nonlinearity, you can change and you can use, for example, Newton line search. The normal displacement increment is fine, I keep the same. Now in this case, since I applied an imposed displacement, I can safely do a load control, even if I expect a strain softening, because the imposed load is not actually a load, it's a displacement. Otherwise, of course, you have displacement control, you have arc length, you have many other things. Now, for the moment, load control is fine. This one is not necessary anymore because after this analysis, we don't have other analysis. And let's say we want to be slightly more accurate here, so we want to use 1,000 steps. But our ramp goes from 0 to 1. So if we want to use 1,000 steps, the lambda should be 0.001, so that the number of steps times this lambda increment is equal to 1. So basically I go here, I save it, and this one is the entire process you can use to create a pushover analysis. Now, the geometry here is very simple. I spent a lot of time explaining all the components. In the next example, I will go much faster. Okay, so the next step, as I said before, up to now, you have been working on a geometry, on a surface, okay? Not on an element. Now, in this case, it seems like you're working on an element because the model is very simple, but you will understand it later on when we will be doing the shear wall example. But in general, the next step is to go under mesh and to decide how this geometry will be converted to a mesh. So the first thing is, for example, to define a global seed. What is the seed? If you're familiar with Abacus, this is the same word they're using. A seed is the typical dimension of the mesh along the border, okay? We have many settings. By default, it is uniform by division with just one division for each geometry, which is fine for frames. If you want to be more accurate, now in this example, I just need one element. But let's say you want to be more accurate for some reason because one element is not enough. You can choose many others, uniform by size, biased if you want to concentrate the element in some portions, and so on. So uniform by size, say for example, I want to use a dimension of 250, you define it, you assign, so you have a preview of the mesh size, and you press done, and then you mesh it. Now in this case, you generated, as you can see here, 12 nodes, 15 nodes, I cannot read it from here yet, and 12 elements, okay? Now this is the next thing, because basically when you mesh it, everything that was assigned to the geometry is automatically converted to the mesh. That's why it is much better than working with mesh directly. Now in this example, I just want to use one element, so I choose uniform by division, assign, done, and then I do a mesh. Now, since it is a beam element, it is not necessary to define the mesh controls, but if you want, you can also define mesh controls for faces and solid, where you decide if the mesh should be structured or not, if it should be triangular, tetrahedral, or quadrilateral, hexahedral, the order of the interpolation, if it should be linear, quadratic, or serendipity, and so on. Then, of course, you have a last option, which is the partition, which is necessary for parallel analysis. So we'll be talking about this Wednesday, not these days, okay? So for the moment, we are going to work with the sequential version of OpenSees. Okay, so we just did the mesh, we are fine, we can run the analysis. So we go here, we choose under our models. In this case, we can use the sequential solver. So we choose OpenSees, not OpenSees MP, because OpenSees MP is the parallel one. Now, when you are here, first of all, let me save it. You have two options. You can just write the input file. For example, let's say that you don't have OpenSees installed on your computer. You can just write the input file, then you send the input file to your colleague that has OpenSees, and you run the analysis. Or you can just click run analysis that basically first writes the input file into the folder where you are working. For example, in this case, I'm working in the one RC column. Here, as you can see now, I have only the input file for STKO. When you will be writing the input file, for example, and by default, I'm here in the same folder where is this file. Okay, basically it has written everything. And if I go here, RC column, I have all my Tcl files. So if you are curious or if you know OpenSees and you want to change something, you can go here and open each one of them. If you don't care about it, instead of writing input file, you can just click run analysis that basically first writes the input file and then runs the solver that you have chosen here. Okay, so in this case, I click run analysis. Okay, it will take like 20 seconds. Okay, so the first analysis is done. Of course, it's very fast because it's just one element. So here we can go to the post processor. Now, if we go on this folder, you can see that now the analysis created these two files. Okay, this one, the large one, the MPCO file, is the database. Okay, the database of all the results we requested. While this one instead is a simple support file that says how the elements are oriented or what is the cross section, because there are some information that cannot be obtained from OpenSees, but they are just information for visual appearance. For example, if you want to see exclusion and this stuff. Oh, keep in mind that this single file here, which is not mandatory, but it is nice for a correct visualization, is only available if you created your Tcl file from STKO, because this one takes some information from STKO. You can still create your Tcl file manually without using STKO and making it create the output for STKO. But in this case, you will not have this support file. Okay, so when you're done, you are in the post processor. You can call OpenDB, which is Open Database. This one is something else I will explain you later. So Open Database, and you go on the folder you're working on and choose result.mpco. Okay, now when you load when you load a database, you have it in the list of your databases. Here you have all the stages of your analysis and all the list of the results. But this is you will never have a look inside this node here, just if you're curious. But whenever you load a new database, you will automatically create a new plot group and a new plot. So you will understand what is a plot group and what is a plot. Now let me remove it so I will show you. Now typically when you open the post processor of a software, you just need to tell what is the output database, and when you open it, you soon have a plot, okay? Because in many software, you cannot create different plots that overlap one another. Instead, here we decided to follow a different approach. We want the user to be able to compare different results, to do different things. So you have to do some extra steps. Now, as you can see, when you open a database, you don't have anything, or the default deform shape, which is not necessary, so I get rid of it. The first thing that you have to do is to create a plot group. A plot group is simply a group that can contain many plots in it, okay? And these plots can be synchronized for comparison, for example. Now, in this case, I want to create a surface plot. I can do it from here or here. These are the kind of plots that we have. So we have the deform shape, the surface plot, which is the same, but with the color map, the volume plot, which is useful for people analyzing volumetric data. So if you want to see what's going on inside the volume. The Gauss plot instead is useful if you want to see the correct results at the Gauss point. So here it will create a particle output that has one particle for every Gauss point. Fiber plot is the same of the Gauss plot, but for fibers. And then you have the vector plot. Okay. Now in this example, let's start with the simple one, surface plot. Okay. So I will explain you how it works. Whenever you create a plot in a group, if you select the plot here, you will see the editor that changes. And in the editor, you have all the parameters. So one of them is the data. Data contains some other attributes, which are the source database, because here we have only one database, but you can have many databases. So you can change the source of your plot at runtime whenever you want. Then you can see the stage. For example, this one is the stage 1, but I want to see the second stage, for example, which is here. Then I want to see, I don't know, the results that you want to visualize, displacement or all the others, the component that you want to visualize. And then you can choose the deformation result that you want. Any vectorial results can be used as deformation. Then you can move through the steps, either here, or of course you can choose the deformation scale. Okay. Then you can move, probably this is too much. And then you can move through the time steps, either manually in this drop-down menu if you want to go to a particular time step, or you can go on the plot group and create an animation, okay? You can create an animation here, or you can just move the slider, okay? And then you have a few other options. You can change the kind of plot, you can use your custom one, you can set the maximum, minimum, you can set what you want to visualize, if you want to see the faces, if you want to see just the edges and so on. Now this is not so much important. I want to show you just the concept of adding multiple plots. So why would you have multiple plots? Because for example, let's say I want to visualize the surface color map of, let's say, the section forces, and I want to visualize, for example, the bending moment about the z-axis. Okay, so here I visualize the color map for the bending moment, but at the same time, I would like to visualize a vector plot for the displacement, let's say. So I can create another plot inside the same group. I call it vector plot, okay? And then I say, okay, but I want to see second stage direct components of the displacement, okay? So this is perfect. And then you can change, of course, all the things here. And then when you do the analysis and make it deform as I did for the previous plot, which is 10, okay? Now, as you can see now, they seem not synchronized, but this is because they are different time steps. Now, but when you go to the group here for the plot, you can see them synchronized, okay? Okay, so this is the vector plot, I don't need it. And now we'll show you something else, which is the feather plot. Oh, first the Gauss plot, okay. So the Gauss plot basically is the same, but creates a series of particles, one for each Gauss point, at the correct location of the Gauss point, where you can see the result at that Gauss point. So for example, if you want to see section deformation, and I want to see the curvature about the z-axis, it is here. So when I do my animation, I will see the curvature that at the beginning are 0 in the vertical analysis, then they are linear, and then finally you have strain localization, and then the curvature is very large only at one Gauss point. Okay, if instead, so here you can understand what's going on inside the force-based element. As you can see, the curvature do not remain linear or compatible with the displacement. Instead, what remains linear is the bending moment. If I go under section forces and I choose mz, so the moment about the z-axis, this one remains linear, which is basically the difference between the force-based, which is based on the equilibrium, instead of the displacement-based. Okay, so you have the Gauss plot, and then the final plot that you may want to see, which is quite interesting, is the fiber plot. The fiber plot, once again, creates some kind of representation at every Gauss point, but this time, instead of being just a particle, is the actual set of fibers at that Gauss point. And this is necessary, for example, if you want to see the stress state instead of being the real stress state. So in this case, I'm visualizing, for example, stress. Well, let me see the strain first. Okay, so strain, this is already at the end of the analysis. Well, probably 10 is too much. Okay, this is fine. And once again, as you can see, if I go and animate this, first the deformation are linear, and then soon it localizes into just one Gauss point. Okay, as expected and compatible with what we have seen with the Gauss plot. And then if you want to see the stresses, of course, you go under stress and you say, okay, but why is it all uniform? It's just because the stress now is dominant in the rebars, but of course you can switch off some of the materials, and I think the rebars was the second material. So if I switch it off, okay, you see just the stresses into the concrete. And here you see the difference between the crashing in the core, but not yet in the cover, sorry, but not yet in the core, because it is still, it is stronger because due to confinement. Okay, and also here you can see what's going on inside the beam. You can either move the slider or use the animation video and so on. Okay, so this is what's going on inside the beams. Okay, you can move while the video is going. You can stop whenever you want. You can just move it manually. Okay, back and forth. Okay, so this is the beam fiber plot, the last plot that I wanted to show you. So here I gave you an overview of all the output that you can have. Now, of course, these are the visual outputs. Then you can export some data. For example, this one is visual, so it's fine for the first visualization, so you understand what's going on. But if you want to know exactly what's going on in a point, you can, of course, extract some data from this. Now, in this first step, so this one basically is the result of the distributed approach, okay? So I want to do a couple of things. Let me go to the Gauss plot. Or just before going to the Gauss plot, I want to go to the surface plot. And the first thing that I want to do is to export the force versus reaction diagram, okay? So I click on show nodes so that I can see the node up here. And I go under extract chart data. When I'm under extract chart data, I can choose, here I have a wizard that will guide me through the export of this data. I can choose to extract data from nodes, from Gauss points, or from fibers. Now in this case, I want to plot force versus displacement. So it is sufficient to say on nodes. Then I click next. And I have to choose the source database, which is the only one I loaded. Then the stage, which is the second one. And then I want to plot in Y the reaction force along the x-axis. And in X, I want to choose a result, because otherwise I can plot a result against the time step or the time step PD or against another result. Now, this other result is the displacement, so it is fine for me to use this set. Then I click next. The next step is to perform the selection. And I want to select this node here. Why? Because since I applied the displacement here, at this point I have both the displacement and the reaction. The reaction is the actual force that I need to apply the displacement. Okay, so it is the database one, node two. Okay, this one reflects the selection that I've done. So I click next. And finally, you can choose the name of this plot. I call it just FU. And eventually, you can create a chart data. Then you have a few other options that now are not important. I will explain you when it will be important. So next. And this is my output, force deformation, okay? Now you can do something different. Let's say for some reason I need an output at the Gauss level. I want the moment curvature response, okay? Because the next step will be to create a lamp plasticity approach. In a lamp plasticity approach, I want to use a phenomenological spring that basically tries to mimic the moment curvature of this fiber. So how can you do this? Well, you remove this one. I create a Gauss point. As I told you, in the Gauss point, you can see what's going on inside a single Gauss point. So if I want to know the moment curvature behavior of my section, I can just go here and I say, okay, I want to extract at this Gauss point, which is the one that is more strained. I want to extract the moment curvature response. Now, this time, moment curvature is a response that is stored at the Gauss point level. So I cannot choose on nodes. I need to choose on Gauss points. Then I click on next. I choose the second stage, which is my pushover. Once again, I want to use a result, and I want to use section force, section deformation in the abscissa, choosing the curvature about the Y local axis of the beam, and the Z local axis of the beam. And here the forces is fine, and the moment about the Z axis of the beam. Next, the Gauss point was already selected, so it appears here. Next, and let's call this one moment curvature. Next. Okay, so this one is my moment curvature response. Okay, now this one can be useful. Of course, you can do the same for fibers, but now it is not important. Why did I choose to export moment curvature? Because the next step, and you will find this file in the folder that I will send you at the end of this webinar, which is called RC column. You have a support Excel file. Now, if you open it, we have some tools here that will be useful later on when we will be doing the lamp plasticity approach. Now, for the moment, you can get this output. You can go to the chart data, so you have the actual data here. You can copy to the clipboard, and then you can paste it here. Actually, if you see this Excel, I already did it. So this one is the moment curvature response extracted from STKO. Now we will come to this in a while. So this one is the distributed approach. Now I go back to my model, and now I will be slightly faster, otherwise we waste too much time in modeling. The next step is to create the lamp plasticity approach. Lamp plasticity approach, we can follow two different approaches in OpenSees. One is called the finite length lamp plasticity approach, and the other is the zero length lamp plasticity approach. Now, the finite length is very similar to this one, and you don't need to change so much. I will show you why. Let me first create a copy of this geometry. So I go under copy, and I copy it along the x-axis of a certain amount. It's not important. Okay, so here I have my second geometry. As you can see, I created the geometry as the property already assigned. If I go in property here, okay, I need to reassign the local axis. So I select this one and I reassign the local axis because it is not necessarily the same. Okay. Then I go under condition. As you can see now, when you copy, the conditions are not copied by default. We decided to do it like this. So if you want to assign this condition to the second geometry as well, it's quite easy. Now you go under the fix, for example. I edit it, and while this is open, I can change the selection. So this one is already selected. I also select this one. When I press OK, now the condition will be applied on both nodes. And I will do the same for the vertical load as well. So I go edit, I click on this point and press OK. So now the vertical load is on both of them. And same for the applied displacement. Edit and apply. Oh, for some reason, I'm not using the full screen, sorry. Okay. Much better. Perfect. Now the physical properties and element properties have been copied, boundary conditions as well. Here, I don't need to change anything because the boundary conditions are already applied. I just needed to assign it to the second geometry as well. Now, this one, as it is exactly equal to the distributed approach. Now I want to convert it to a lumped approach, the lamp plasticity approach. Now, this time we will use now, when you do the lamp plasticity approach, you understand that you try to lump your nonlinearity into certain points. Now, in the case of a column, to the end of the columns. And then you have a problem. How you define this moment curvature behavior? Now, in the finite length approach in OpenSees, you can still use a fiber cross-section, which is not actually lumped into a zero length interface, but it will be spread over a finite length, which will be equal to the plastic hinge length. And this one it can be done using a particular element, a particular integration scheme that you have in OpenSees, which is called the hinge radal. Okay, so now I will show you. Basically, in this model, we will be using the same fiber cross section and internally an elastic section. Okay. So let me first create an elastic section. Okay, elastic beam. I go under section, elastic is 3D. I define a section profile from here, and I choose a box, and this box should be 500 times 300, or the opposite, sorry, 300, 500. Yes. Okay, so here I have all my my elastic properties, my mass properties of my section. Press OK, and here I can enter the material properties, which will be the same for concrete but elastic. And here we'll make a mistake. Now I put the entire elastic property of the concrete, which is to be compatible with the other one, 35,000. Too much. And let's say 15,000 for shear, but it is not important here. Now, if I keep this one, I will create a mistake. The results will not be the same. Now, let's see what's the difference. So let's start with this. I press OK. So this is my elastic beam. And now I need to create something like this, the beam property, but for the finite length. So I create another one and I call it beam property finite length lamp. Okay, I go under section, special purpose beam column, beam section property. Now in this case I go under hinge and I choose hinge rad out. There are many others. If you're interested, there is a paper by Professor Scott that explains what's the difference between one and the other. This one, let's say, is the best one. So here you can choose the section that you want at one end of the beam, at the first end, and I want the fiber section. The same for the end J of the beam. I want the same fiber section. Then I have to specify the LPL of I and J, which is the plastic hinge length. And in my example, I will use 150 and 150, which is exactly equal to the integration weight of the Lobato scheme here. So if this is all correct, I should obtain the same results. And for the internal element, I can choose another section that can be either the same fiber section, but then I've not done anything basically, because I don't gain anything from performance. The performance here is that the internal element can be treated elastically. So the three integration point in the middle will be elastic, and the nonlinear integration point will just be at the ends. So I choose the elastic beam that I defined before. I press OK, and I assign it to the second geometry. Okay, now as you can see, the representation is slightly different. You can see here that I show you that these two integration points that here are represented with the exact length, integration weight, they have the beam fiber. While in the middle, the representation is different because they have the pure elastic section. Okay, so now the next step would be to create another element property, but it is not necessary because this lamp plasticity using the finite length approach behind the scenes is still a force-based beam element. Just the integration scheme has changed. Okay, so I can use the same element I've used for this one. And I'm ready to go. I can save it. Since I changed the geometry, I need to remesh it without changing the settings because they were fine. So I rebuild the mesh. Now I have 4 nodes, 2 elements, and I can run the analysis again. When I run it, it will overlap my previous results. Okay, I changed something because now this one was not, okay, it's not converging, but because I changed the results. So I'm going to show you. As I told you, there was a mistake in the second database. Okay, so let me show you the surface color map. You see now 2 of them. Yeah, the surface color map is fine because now I want to show you the results of moment versus displacement. So let me extract a result. A moment curvature, I don't need it anymore. So I want to extract on nodes, same thing I've done before. Stage 2, I want to extract displacement versus reaction force at this node and also at this node. Okay, so I go to next. I have 2 nodes. The number 2 is the first one. The number 4 is the second one here. I click next. This one can be called FU. And here it is important now, this output here. By default, it is keep multiple results. This basically will create 2 overlapping graphs, one for each node. Otherwise, you have the option to do an add, an average, to compute only the maximum or the minimum. Now, in this case, we want to compare them, so we choose keep multiple results. Okay, now as you can see, there is a difference here. First, the analysis has stopped for some convergence problem here, but this convergence problem comes from this beam element here. You can see that the stiffness is not the same. Right? This is pretty obvious because if I go under the beam fiber section, now in this case, in the middle, it is elastic, but I'm not taking into account that actually the concrete is cracked for a huge portion, because in this example, I have a very small vertical load. So in fact, if I plot the strains, in all the first stage of the analysis, half of my element is completely cracked, while in this case it is not. Okay, So how do you change this? Well, there are many, it's not something, it's one of the drawbacks of the lump plasticity approach. You have to do some assumptions. Then you have to understand how this elastic property can be reduced. But it can be done pretty easily here in STKO, because you go under the elastic section and you can choose either to change the Young modulus, but this one would not be correct, because if you change the Young modulus, you change also the axial stiffness, which instead should be the same, because in compression it is all reacting. So you have the stiffness modifiers for the bending stiffness in Z and Y. Now, in this example, I found that the 35% of the total one was fine, so 0.35, 0.35. Okay, let's save it. Now you can use whatever code you want. I think national codes give you guidance on how to define this reduced stiffness. Okay, so let's rerun the analysis. Now they should be the same. I don't have any convergence problem. I reload this, and now when I reload this, since here I have linked to the database, this data will be updated automatically. So here I will see the updated graphs as soon as I do reload. Okay, and as you can see here, the results are basically the same. There is a slight difference due to the 0.35 assumption that I did. Of course, you cannot get the exact number, but the results are basically the same. So you can see what's going on in the moment curvature analysis, same localization at that point. Of course, this one is much more performant because it has 3 internal Gauss points that are elastic. Instead here, there are more than the double number of Gauss points. So what's the advantage of this lump plasticity approach is that it's basically performance. The only drawback is that you need to calibrate these internal elastic parameters here. And the other advantage is that since you're using fiber cross-section, there is already interaction of PMM, and this nonlinearity is correctly spread over a finite length which is exactly equal to the plastic hinge length. Now in these two examples they are the same, but now imagine that these beams are not 3 meters but are 3.5 meters, and the plastic hinge should be always 150. Now this one should give me a wrong results because the integration point here will have a larger weight. So I need to regularize this one manually. Instead, in this case, it is exact because it has a finite length. It is always the same. It is not dependent on the length of the element. Okay, so this is the lump distributed approach using a finite length. Now the next step would be to create the lump plasticity approach with a zero length interface. Okay, so I can go back to the preprocessor and make sure my file is saved. Now, what do you think we can do? I think we have a coffee break here scheduled. Guido, do you think it's fine to do the coffee break now, 20 minutes, and then we keep on doing with this example and then the shear wall?